Hello. We have been discussing about biconjugate gradient method for solving linear systems of equation. This is an iterative method, and this method has emerged from the inspiration we got from conjugate gradient method, that is a Krylov subspace method can be devised for symmetric matrices in case of conjugate gradient method, which is a very fast method and also very simple to implementation method. Now, the problem with conjugate gradient method was that it is restricted only for symmetric matrices. So, we thought of developing a method which is for asymmetric matrices or for any general matrix, and for that Langso's biorthogonalization method has been developed, which we have discussed in last few classes. And in Langso's biorthogonal method, we start with the Krylov subspace method, subspace of the matrix A as well as of the left matrix, which is A transpose. And we have seen that how this method has been developed into biconjugate gradient method, which will supposed to be to give a convergence rate which is kind of similar as the conjugate gradient method. And now we have discussed up to the development of biconjugate gradient method in our last class. As I said, biconjugate gradient method is a iterative solver which is inspired from conjugate gradient method. However, this is applicable for any general matrix. It is not only strictly restricted to symmetric matrices as conjugate gradient methods were that. So, if we look into the biconjugate gradient algorithm, which we were discussing in the last session, that this is directly copied from Yusuf Sar's book, and we can see that this algorithm has a number of matrix vector multiplications. As we have discussed earlier, matrix vector multiplications are the most costly operations in matrix solvers, and if even if we can bring down the number of iterations, but if number of matrix vector multiplication is each iteration is quite high, it will take a lot of time to give the results. So, we usually try to reduce the matrix vector multiplication. However, if we look here, that the first matrix vector multiplication is for getting the initial guess, which is not required at the later iteration stage throughout but the later matrix vector multiplication like this, finding this A p and finding this A transpose p, they are done again and again. Whenever we go to one new level of iteration, we have to do these two matrix vector multiplications. So, two matrix vector multiplications are associated here, which is, if we think compared with SOR or Gauss-Seidel type of method, it has only one matrix vector multiplication in each iteration. So, number of mathematical operations in each iteration is high in one sense. However, there are few other issues. One important issue is that there is an A transpose P multiplication, and we will discuss later. This multiplication is not only a matrix simple matrix vector multiplication, rather a matrix transpose vector multiplication. So, given a matrix, I have to rewrite the code to do a matrix transpose vector multiplication, because when we have seen the programming implementations or the code implementations, we have seen that there is a subroutine which does the matrix vector multiplication, and this subroutine is called again and again when we need this multiplication. However, that particular subroutine will not work, rather we have to write a different subroutine, which is also not of that much problem, but the problem may be that when we try to access the matrix A, we first access row wise and then we are increasing column wise, but when we will think of A transpose P, the access of different memory elements of A will be completely changed, and in some of the computational framework it creates significant amount of problems. There is another very serious problem here, that if I look into the term alpha, alpha is obtained through r dot r star. R star is the residue in the left space or A transpose Krylov space, and R is the residual of x is equal to b, divided by a dot product between A p and p star. P star is again auxiliary vector in the left Krylov subspace or Krylov subspace of A transpose R 0. Now, A p this is one matrix vector multiplication I am doing in AP, which is used to calculate alpha. When we are calculating R j plus 1, we are doing R star j plus 1, which is the new residual in the A transpose Krylov subspace. We are doing this multiplication A transpose P star, which is, I said, it is difficult multiplication, matrix transpose vector multiplication, and multiplying it with alpha. What is the implication? Implication is that we have earlier discussed about round-off error. I do some numerical calculation, I multiply the 3.33333, that means say 10 by 3 into 1 by 7. I really do not get it as 10 by 21, rather I get a numerical value, and this numerical value is not something like an infinitely long decimal. After certain decimals places, this value is truncated, and we accrue some round-off error. So, one round-off error is accrued here, because matrix vector multiplications has lot of multiplications and additions, and so the round-off errors will be built up to some substantial value. Otherwise, round-off errors for one single operation, it is very small, but when we do thousands of operations, they add up, and there is those small some value added up here. Now, we are doing some we are encountering some round-off error in this step. Alpha is carrying this round-off error, and when we are coming into the R star j plus 1 step, this round-off error is again being multiplied with the round-off error, or again being added to the round-off error through our multiplication, which is obtained by multiplication of A transpose into P star. So, the error is actually building up, and then we are dividing R star by doing this calculation, again taking dot product, dividing it, all these divisions, multiplications are adding up round-off error. So, there is some conjugacy between the round-off errors which is building up, and that is a serious issue in biconjugate gradient algorithm. As a matter of fact, this is from my personal experience. If I try to write a code on this and run it, this will not run in a single precision machine or with single precision variables. I have to define all the variables to be double precision, so that I can give I can reduce the round-off error to a much smaller value, and then only this particular algorithm will work. However, there can be cases that even with double precision, this algorithm is failing for certain type of matrices, and that is the main concern, especially that will devote this particular lecture on seeing that what are the issues of the round-off error, issues that the round-off error is creating, and also what are the remedies for it. Okay. So, the issue is that irregular convergence is observed due to rounding error with increased computational operations. Another important thing is that convergence is not very simply defined for biconjugate gradient algorithms. We can understand that this algorithm comes from approximating the basis vectors in two Krylov spaces. One is Krylov space of A transpose A R 0, R 0 is initial residual. Another is the Krylov subspace of A transpose R 0, and we try to approximate the solution in both the subspaces and generate more basis vectors and finally converge to the right result. What happens in this stage is that error is some way a function of how the eigenvectors of both the subspaces are well approximated, and we see that the residual in one subspace depends on the eigenvectors of the basis functions we obtained in the other subspace. So, we can see that none of the all the parameters, like all the residual parameters, are dependent on the other subspace in the algorithm. So, what happens that we cannot write a strict convergence criteria that error is always less than the error or residual is always less than the residual of the previous iteration for these cases. Then we will see that there are some oscillation of the iterations, and when the residual value is quite high, the rate convergence is good, and when the residual value reduces to a small number, the convergence slows down. These things make these methods are little more complex, at least the results of this method to be represented in which looks little more complex, and we see that there is an oscillation in the residual when it is converging to a small value. And if there is a round off error, if there are high round off error, this oscillation sometime does not converge to a right result, and sometimes this round off error builds up and blows the entire calculation, it does not converge or it converges to a wrong result. So, this is typically identified as numerical instability. We call this to be a numerical instability of this particular method, by conjugate gradient method. So, we need to find out the remedies how to take care of that. So, the issues are that two matrix vector product in each iteration makes it computationally costly. Also, it might be difficult to multiply a transpose matrix with a vector. We are deliberating on this point in the last slide, that when we do the multiplication, say we are writing say A into B. So, each element in a row of A is multiplied with corresponding element in the column vector B. This is multiplied with this is multiplied with this, and they are added. So, if we think of a computer, how is it doing that? It is going into the memories in this memory space. Computer stores everything in its RAM, and it starts with a pointer which moves around the stored values. So, it goes into a particular memory location and takes this value, and goes into the memory location of B and takes this value, and then the control goes to the next memory location, also both in the row of A as well as in the B vector. So, memory access is kind of in a contiguous manner. A contiguous system of memory is being accessed everywhere, especially when we think of using high performance computing architectures like GPU cards. This is important, that how this memory is being accessed, because memory to computing core bandwidth is very slow there. Now, if I have to do A transpose B, instead of multiplying B with the row elements of A, I have to go column wise. However, the storage algorithm that I write for A, or the way I try to have my computer access the memory of A, is based on doing AB multiplication, because matrix vector multiplication, what do we do, matrix addition, what do we do, or matrix vector multiplication, what do we do regularly. So, there is a different nature of memory access which will be required, which can be difficult as well as much complex from computational aspect. It can kill down the performance. Another thing is possible, that sometimes we do not form the A matrix explicitly. There are cases when we are dealing with very large system of equation, we do not store the matrix. We go to each row and see what are the neighboring values. If we can recall how the matrix is formed from finite difference or finite volume or finite element method, we go to one element and see all the neighboring values, and then do the required multiplication with the variables given. In that case, A is not formed explicitly, and getting A transpose is also extremely difficult. Sometimes it is impossible, because we are not forming A explicitly, we are somewhere getting the products A B, but that is through the equations, through each linear equation, we are not forming the matrix A transpose. So, this gives certain overhead, and sometimes it becomes impossible to handle the systems. In cases when the matrix is not explicitly stored, it can be impossible to multiply the transpose. Further difficulty may arise due to memory management, and we is discussing this. And the important thing is that when we discuss about GPU computing or doing high performance computing and using good memory coalescence, writing efficient kernels for GPU computing, which needs lot of algorithmic tweak considering how the memory is being accessed and how data in terms of memory, how data is shared by different computing cores when things are going in parallel. There this transpose vector multiplication can really be a limiting step. Also, the numerical instability that is due to accrued round-off errors, numerical instability can kill the final algorithm. And furthermore, there is one issue which is complex convergence relations involving W and V, involving both the vectors Krylov subspaces, because it is not restricted to only one Krylov subspace. There is another Krylov subspace which is important here, and therefore, the rate of fall of residue is in a complex manner, and we see an oscillatory pattern here. I will show you at the end of this, and the next lecture I will show you some of the results using biconjugate gradient method, and you will see that the residue does not monotonically drop down to 0, rather oscillate due to the complex convergence pattern. So, considering all this, that this is an oscillatory method, on top of that there is some numerical oscillation, the entire method might give us some wrong result. Also, there can be implementational issues due to matrix transpose multiplication. So, two things have to be seen. One is that how we can avoid the matrix transpose matrix into vector multiplication, which is very important in terms of the actual performance of the solver, because we are only discussing till now, we have only discussed about how many iterations it will need and what are the computational costs, etc., but we have not discussed, which is little more computer science aspect, importance is there in computer science aspect, that is the performance of the solver in terms of memory handling, in terms of the fact that how the processors are getting data from RAM and how efficiently it is using the cache, and also the high performance computing or GPU computing aspect. Memory handling is important, and when you are doing a transpose matrix and vector multiplication, this memory handling is very complex and it might stop the entire process. Also, as the algorithm is developed, sometime we can very easily see that Gauss in a Gauss Seidel iteration method, we may not write it in the matrix form. We can take each iteration and try to find out the updated value from a guess value. Right? If you think of a Gauss Seidel iteration, you may not write the entire matrix form, you just write the equations and use the equations for the iteration for getting the updated value based on a guess value. So, there can be cases when we are not explicitly forming the matrix, rather we have sets of equations, because explicit formation of the matrix also need a data structure, how the neighboring, what are the relations of neighboring nodes in terms of IJK rectangular arrangement, which is not present in certain cases. There finding A transpose is impossible. So, there are certain cases for which biconjugate gradient, though it has tremendous potential in terms of the due to the facts that it is applicable for any general matrix and it is a Krylov subspace based method which can very fast give us the solutions. Though these potentials are already there for biconjugate gradient method, it can have these few problems. One is that implementation wise there can be a problem due to A transpose B. There can be a problem in terms of the code performance due to memory management of A transpose B, and also as the round-off errors are increasing, as well as the method has a complex convergence pattern or oscillatory convergence pattern, there can be another problem. And why the round-off error is increasing? Because matrix vector products are giving us round-off error as large number of multiplications and additions are involved there, and one matrix vector product is further being utilized to get and being multiplied with another matrix vector product to get that Rj plus 1 star. So, matrix vector products are in a way coupled, so that the round-off errors can further accrue up, and we can have lot of numerical errors, numerical oscillations, along with the inherent oscillation of the scheme when the residual value is coming down. So, where residual value is very small of 10 to the power minus 8, and I am getting round off error of the same order, so 10 to the power minus 9 again. So, it will be difficult to get the method converged, because even when the round off error is when the residual is falling down, the cutoff value or the epsilon, the round off error is substantial, so that it does not allow the residual to fall down, and it might converge to a different result also. So, all these issues are there. So, we have to see that how we can get ahead with we can get away with the transpose matrix and vector multiplication part, as well as how can we reduce the round off error, so that one matrix vector product is decoupled from another matrix vector product, they are never multiplied together in a sense. So, it will be important to design similar algorithm similar to BiCG biconjugate gradient or BiCG algorithm with less matrix vector product steps involved. It is also, is it possible, the question is it possible to eliminate the transpose matrix and vector product? This is one of the limiting step implementation wise, some cases memory wise or the performance wise, can we eliminate this step? Whatever we do, finally the vectors produced by biconjugate gradient method must satisfy the following two orthogonality properties, that is Rj dot Ri star. Rj is the residual of Ax is equal to B, and Ri star is the residual of A transpose X is equal to B star something. They are orthogonal to each other. If I is not is equal to j, they are 0. Similarly, the auxiliary vectors P of A and A transpose are A orthoconjugate. That means AP dot P star is equal to 0 for I is not equal to j. We have worked on these properties, explicitly have shown how to derive these properties, and this is the basis of biconjugate gradient method, that these two conjugate properties, these two orthogonal probability must hold. So, can we get these two properties even without going into so many matrix vector products, as well as avoiding the transpose matrix vector product? So, it will be required to obtain these vectors Ri and Rj in functional form, where instead of doing A transpose, we can probably have some functional of form of R and P, say a polynomial form of R and P, so that the dot product does not necessarily inverse transpose of a matrix. So, the idea will be that instead of forming the vectors as a simple column vector, we will try to express these vectors in a polynomial form, and we will try to take the dot product and other operations in the polynomials only. So, that these polynomials are never explicitly formed, but only the polynomials are used as certain basis to create these vectors, so that we can avoid the computational complexities of biconjugate gradient method. And so, what we look for is a transpose free variations of this method. Transpose free variation means, as it says clearly, that this is designed to avoid matrix transposes which are in the biconjugate gradient, usual biconjugate gradient. So, this method starts with assuming a polynomial form of the residue vector. That is, we start with R is equal to the initial residual vector R0 based on the gas value, and at any iteration level the new residual vector Rj is R0 multiplied with a polynomial of the vector of the matrix A, phi j into A0. So, it might look little difficult to appreciate how a polynomial of a matrix will look like. A polynomial of a matrix, a polynomial of a scalar will give us a scalar, a polynomial of a matrix will give us a matrix. So, finally, it is a matrix multiplied with R0. That is, the jth residual vector is obtained by multiplying a jth order polynomial of matrix A, phi j is a jth order polynomial, with initial residual obtained from the guess value. This polynomial is defined as phi j 0 if I instead of a like this polynomial can operate, this is an operator, this can operate on a scalar as well as it can operate on a vector or a matrix. So, if I write say phi 2 is equal to phi 2 of t is a scalar, phi 2 t is equal to a t square plus b t plus c. So, phi 2 of the matrix A will be A into A square, which is A into A, plus B A plus instead of, so there is a there is some matrix C, some matrix C. So, here it is a scalar C, here it will be a matrix C, and that there is exactly that phi of 0 is a scalar 1, but if I put a 0 matrix instead of phi, the polynomial will give us a matrix which is an identity matrix. So, phi 0 R is A is equal to 0, that means all the elements of A are 0, then R j is equal to phi j R 0, and this is identity matrix I. So, R j is equal to R 0. So, this is the same operations which we are supposed to do over a scalar, we are now doing it over a matrix. So, now what is done is that similarly polynomial can be also assumed. Earlier we saw we are assuming a polynomial form for the residue vector. Similarly, we can assume a polynomial form for the auxiliary vector also. Also in the W space or the A transpose space, vectors can be assumed of similar form, that R j star is phi j A transpose R 0 and P j star is pi j A transpose R 0. Phi and pi are two polynomials, two different polynomial functions, and when they are operated over A, they give us phi j A into R 0 give us R j, and phi j A transpose R 0 gives us the residual in the left space or the A transpose Krylov space, which is R j star. Similarly, for the auxiliary vectors we get the polynomials. Now, in a BiCG, typical BiCG algorithm, alpha j and beta j are defined as alpha j is R j star A p j star, or dot product between R j and R j star divided by dot product between A p j and p j star. Similarly, beta j is R j plus 1 R j dot product with R j plus 1 star divided by R j dot R j star. And what we will do is that we will try to replace this by the polynomials expression of the residue and the auxiliary vectors, and we will see that if in some way we can eliminate some of the matrix vector multiplications, mostly we will try to eliminate the matrix transpose vector multiplication through this. We will see it in the next class. Thank you.